All right, so I do have quiz 2 here today, but for the first half, I wanted to go over a little bit of a review for what we're going to be doing after the midterm. Remember, on Monday we've got our review, on Tuesday we've got our midterm, and then after that we're going to get into graph algorithms. But since we've got a good chunk of time before the midterm, and to relate it to work that you're doing for homework 2 right now, I did want to give you a brief review on stuff that you probably covered in 235 and 156 that will, as a refresher, will help you with possibly with your second homework. So today we're going to, in the next 45 minutes or so, we're going to review graph representations and basic tree traversal algorithms. Tree traversal algorithms that you're familiar with already: pre-order, post-order, in-order traversal. You're going to realize eventually that those are actually just very special cases of depth first search, or DFS. So first of all, representations. There are a couple of ways that you can represent graphs. First of all, in practice, you could use a library, right? But the two basic ways that you can represent a graph are going to be an adjacency matrix and an adjacency list. Okay? So for example, suppose that I had the following graph, right? If I had a graph with 4 vertices and 4 edges, and this was A, B, C, and D, then of course we have an edge set of AC, AD, CD, and BD, and of course those are going to be unordered. If I have an adjacency matrix, then an adjacency matrix is nothing more than an n by n matrix that is going to be 0, it's a Boolean matrix, it's going to be 0 or 1. Now this adjacency matrix A, yeah, I'll go ahead and go with A because it's an adjacency matrix. A sub Aij, the entry, the ijth entry, where I is a row and j is a column, that's going to either be 0 or 1. It's going to be, I should have written it in the other direction, but it's going to be 1 if v sub I and v sub j are connected by an edge. And it's going to be 0 otherwise. Or, in other words, if v sub I, v sub j are not connected by an edge. Okay? That is an adjacency matrix. The adjacency matrix corresponding to this graph over here is, well, first of all, you have to impose an ordering on your vertices. It doesn't matter what that ordering is, as long as you're consistent about it so that you can find what you're looking for. I'll go ahead and go with A, B, C, and D, because that's the natural ordering. A, B, C, and D. So these are going to be 0 or 1 entries. A is connected to, not to B. It's also not, we don't allow self loops usually in graphs. You can have self loops in certain types of graphs. Pseudo graphs is what they call them. But we don't do that in regular old graphs, because if you're at a node A, how do you get to A? Well, you're already there, right? You don't need an edge indicating that you can get to A from A. So we'll end up with 0 over here because there is no self edge, but you can have what are called pseudo graphs, and which do allow self loops. A is not connected to B, so that's 0. B is connected to C, or sorry, A is connected to C, A is connected to D, so these are both 1s. Right? Likewise, B is only connected to D over here, so 0, 0, 0, 1. C is connected to both A and to D, so we have 1, 0, 0, 1. And finally, D is connected to A, C, and B, so 0, 0, 0, 1, or 1, 1, 1, 0. And you'll note, what about this matrix? If I took the transpose of this matrix, what would it be? If I flipped it about the diagonal, what would it be? The same, right? That tells you it's symmetric. Hopefully you remember those kind of terms from 235. This is a symmetric kind of relationship. And that makes sense because this is an undirected graph. A goes to D just as well as D goes to A. Right? That's one way of representing a graph. Another way of representing a graph is an adjacency list, where you have each node, each vertex, has a linked list. This is how it was represented in your first homework, implicitly in that text file, and elements of which are vertices connected by an edge. So again, this graph right here, you would have four vertices, so you would have 4 linked lists, one for each one of those vertices, A, B, C, and D. And in each one of those linked lists, you would have a list of vertices that are connected to it. So A is connected to C and D. Its linked list would look like C, and then the next element in the linked list would be D. And then at that point, it's a termination of that linked list. B would have a linked list, but it'd only have one element in it, D, and then nothing after that. C would be connected to A and D, and don't read anything into the order that I'm putting these in. It could be like D and then A. I was just going in lexicographic order because that's the natural ordering. But you can't read into anything in the ordering of these things unless you impose an ordering in your implementation. D is connected to A, B, and C. So let's go ahead and go B, then to A, then to C. Again, no additional information unless you impose it on the ordering of those linked lists. There's one representation, there's another representation. Why do we have these two different representations? Is one better than the other? And the answer is no. It all depends on context. And to motivate that idea, I'm going to give you 2 problems. Okay? Here's the first problem. Given a graph G equals V comma E, right? And 2 vertices X and Y in V. Output true if X and Y form an edge, false otherwise. Okay? So in other words, this is a basic operation. This is a basic elementary operation to a lot of other graph algorithms, right? How do we actually implement this thing? Well, it all depends on how you represent your graph. If you represent it by an adjacency matrix, or if you represent it by an adjacency list. And there will be a different efficiency for each one of those representations. So here's solution A. Suppose that we use an adjacency matrix. And we'll write pseudocode, input graph G and 2 vertices X and Y, output true if blah, blah, blah. In other words, this thing up here, I'm not going to write it down again. All right? So an adjacency matrix. How do we answer this question? How do we answer that X and Y are connected if it's an adjacency matrix? Output what? All you need to do is output whether or not, let me go ahead and rephrase this. There is a little bit of work here. We'll go ahead and go with I is going to be the index of X, and then J will be the index of Y. You can assume that X and that you were given these instead of generic X and Y. You can say, given I and J, everything is going to be represented as 0 up to n-1, just like we did with your homework. There's a reason for that, because those correspond to indices. And then all we're going to do is, if A sub ij is equal to 1, output what? If it's equal to 1, what does that indicate? Is A connected to C? Yes. So output, true. Else, output, false. Did you see any loops? No. Did you see any, well, there's a condition here, right? I could have just output to this directly, right? A ternary operator or something in real programming languages. But maybe there is some work to find the index of X and there's some work to find the index of Y. Maybe. Again, it depends on how you actually implement these things. Maybe everything is identified with I and J, or maybe you've got a hash table that given these objects, you can hash it directly to an integer. Right? So what kind of work is done here? Because it's an adjacency matrix, all it is jump to row I, column J, and retrieve that value. In other words, this is all going to be order 1. It's constant. On the other hand, if it's an adjacency list, what do we have to do? First of all, we'll go ahead and get the list corresponding to X. And now we have to answer the question. Now we've changed the question, right? If I gave you C and I was going to ask you, well, is it connected to B? What would you have to do? You'd have to go, is that B? Nope. Is that B? Nope. I'm at the end of the list. So I would have to do a linear search on its adjacency list for each, we'll call it Z in L. If Z is equal to the thing that we're looking for, Y here, then output true. Otherwise, if you get through the entire list that corresponds to X, output false. And this is assuming that you've kept track of both relations, that if X and Y are connected and they're in their respective adjacency list, that in Y's list you also have an instance of X. Otherwise, if you don't have that assumption, then you'd have to do this twice. One for the list corresponding to X, and then again for the list corresponding to Y. But this is clearly not going to be constant. Why? I've got a loop now. And this loop is at most what? How big can an adjacency list be? Well, how big was the adjacency list for D? That's the largest one, right? It was 3 in a graph of length, graph of size 4, right? In general, it could be order n for this loop right here. So it matters depending on what you're trying to do with the graph on how you represent it. Some things can be, some problems on one representation can be efficient. Others, on a different representation, it'll be inefficient. And just for completeness, to show you that, well, it's not always going to be best to do a matrix, there's another problem. Given a graph G equals V comma E and a vertex X in V, output either the neighborhood or the size of the neighborhood if you really want to, the size of the neighborhood of X. All right, this is the size of the neighborhood of X. All right. Well, again, an adjacency list, or an adjacency matrix first. If I have an adjacency matrix, and I have an element C here, say, what do I need to do to determine the size of its neighborhood? The size of its neighborhood here is 1, 2 for C. But in general, what would I have to do? I'd have to set up a counter to be 0. Then for J, here I'll go ahead and go with I is going to be index of X. Right? And for J running from 0 up to dot, 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 say n minus 1. If a sub ij is equal to 1, then I'll go ahead and increment my counter. And if you wanted to actually output the neighborhood here, then you could keep track of a set that you started out with the empty set and then you add it each time. I'll just go plus plus. Right? And then output count. Take out that Right? So clearly this is not going to be constant. What do you have to do? You have to go over the entire row and count up the number of ones. So consequently, this is going to be order n. Whereas an adjacency list, well, once you've got the list corresponding to x, what can you do? Output x dot size or x, the cardinality of x, and that's it. That is going to be order 1. Assuming that your implementation of a list keeps track of the size, and that's really easy to do. Anytime you put something in, increment a counter. Anytime you take something out, decrement that counter. Right? So just the flip side. A different problem becomes efficient on an adjacency list. It becomes inefficient on an adjacency matrix. Right? And less efficient, I should say. Order n, linear, that's still going to be efficient. Right? But it does matter with the representation. Now, to wet our whistle for coming back next week on Wednesday, we will, of course, meet on Monday for the review. Tuesday is going to be the actual midterm, but on Wednesday, that's when we'll resume lectures. To wet our whistle for that, I wanted to remind you about some basic graph algorithms. And for now, we'll go ahead and restrict our attention to what you're already familiar with, trees. Okay? So let me go ahead and draw a tree here. I'll just go ahead and make it generic. A, B, goes to C, goes to D. Maybe B has both of its children. E, F. And then F has a right child. G. Okay? Now, I want to do, say, a pre-order traversal of this thing. In other words, I want to go over the tree and I want to keep track. I want to visit every node and process every node. Remind me how you do. Remind me what a pre-order traversal looks like. Pre-order traversal is going to process the root, then the left, then the right subtrees. Right? So I'm going to do a pre-order traversal on this, and then we're going to actually codify this as a full algorithm. So if I come in and I start at the root, then I've got A. I process A, whatever that means. All right? Then I do the left subtree. So now I'm looking at the left subtree here, and my new root of that subtree is going to be B. Then I go to the left subtree, and my new root is going to be E. I process that. I go to the left subtree, but guess what? It's empty. At which point I'm done. I need to start backtracking. Come back up here, and then I do the right subtree, which again is empty, so I end up not doing anything. I come back up, and now I've done the root, B. I've done the left subtree, E, and all of its sub nodes, even though there aren't any. And so now I need to do the right subtree. And so I come over here. Now I've got F and G. The new root of this subtree is F. There is no left subtree to process. So I've done root, left, and now I need to do right. I come down here and I do the root, G. There is no left, there is no right, and so I'm done now entirely with that subtree rooted at B. I've done A, the root. I've done the left subtree, which is at B. Then this entire thing is the left subtree of A. And now I need to do the right subtree. So I come over here, and this is my subtree now. The new root is C. Then I do the left, which is D. And then I do the right. Well, then I do D's left, D's right, but there's nothing. And then there's nothing on C, on the right subtree of C. That's a pre-order traversal. Now, a pre-order traversal has several properties that you may be interested in. just like a post-order traversal has several properties that you may be interested in, and an in-order traversal has different properties. For example, if you have a binary search tree, an in-order traversal is going to enumerate every element in order. A pre-order traversal has a nice property that it's the absolute simplest implementation that you can come up with. And so that's what we're going to talk about with the remainder of today here. And then we're going to adapt it to help you, say, maybe with Huffman coding. So here's a pre-order traversal. Now, how do we design an algorithm to do this? Okay? You can do it recursively. What does the recursion look like? Well, the recursion looks something like process the node u, given the node u, process it, and then recursively process use left child or left subtree, right? So it'd come back up here. U would now be use left subchild, and you'd process it and go left, go left, go left. And then you need to eventually come back, at which point you would come back to this part in the recursion. And then you would recursively process use right child. Right? Doesn't get much simpler than that. And if you are an advocate of recursion, go ahead and do that. Right? You're not, unlike some recursive implementations, like say for Fibonacci, you're not redoing some work here. You're only processing every node exactly once. You are abusing the call stack, but that's not that big of a deal for most graphs. But still, I'd prefer to do it using a smart data structure. One of the themes of 156, at least my 156, is a quote by Eric S. Raymond: smart data structures and dumb code are a lot better than the other way around. So let's use a smart data structure instead. Now, before we do that, let's go understand how to do that by thinking about locally on this tree here. So there's a left child and a right child, right? Now, I want to process this node. Well, okay, go ahead and process it. But then I also need to remember that I need to eventually process the right subtree, but first I want to go ahead and process the left subtree. How do I remember things, right? How do I keep breadcrumbs behind me, right? Hansel and Gretel. Think about Hansel and Gretel going into the woods. They took a piece of bread and then pulled off a piece so that they would keep track of where they went. They went from A to B to C to D. At D, they might become lost. So what do? They turn around and said, where did I come from? I came from C. Okay, now where did I come from before that? I came from B. I came from A, so that they could backtrack all the way back to the beginning. Right? Of course, their bread was eaten and they were lost. Anyway, but that's how you keep track of things. That's why we call them breadcrumbs. Right? You see this also in most websites. Right? Most websites have a menu, right? And then you can go from a top level area, like say UNL, and then you can go to the College of Engineering. Then you can go to the Department of Computer Science and Engineering. Then you can go to a particular faculty's website, right? Or personal web page. Those were breadcrumbs, and they call those breadcrumbs in navigations, right? So that you understand where I want to go back. Right? Where did I come from? So how are we going to keep track of those breadcrumbs? We'll do it using a stack. Why does a stack help us? Remember that a stack is a LIFO order. If I put into the stack, say 10, 20, 30, and 40, I went from starting at location 10, if you want to look at it that way. I went to location 20, I went to location 30, I went to location 40. How do I backtrack? How do I go back to where I began? Well, these are breadcrumbs. And a last in, first out order ensures that the breadcrumb order that you put down is the breadcrumb order that you would pull out. And so last in, first out ensures that you have an ability to keep track of where you went. So let's think about this over here. If I'm currently at A, where do I want to go next? I want to go down here next. But before I do that, let me make sure that I set myself up so that when I eventually come back here, I still need to explore this right subtree here first. So if I've got A here, I've got L and R. What order do I push these children into my stack to keep track of everything? Do I do it left, right, or right, left? Which one's first? Right first, and then left. Why? Because when I pop this out, I'm going left, and I'm keeping track of this breadcrumb out here so that eventually when I come back, I know that I still need to process R. Okay? Here's the algorithm. So my input is going to be a tree, a binary tree, T equals V comma E. Right? And my output is going to be a preorder processing of T. Okay? So I need a stack. I'll just call it S. Here's an init stack. All right. Initialize an empty stack. Okay? That's going to hold a bunch of tree nodes. Now I need to get things started. So where do I get things started always in a tree? The only place that I have it, at the root. So S dot, now what are my basic operations for a stack? Put things in. What's that called? Push. T's root. Now, I've actually tried to look up the history of stacks. Stacks go back all the way to, in the context of computer science, of course, and programming, go all the way back to, I believe, the 40s. I've tried to find why they called it stacks and why they called it pushing and popping. And the only thing that the only reliable resource that I've been able to find on why they did this is because it's like a cafeteria stack of dishes, right? So you've got to, I think if you go over to, say, Celic, they still have this style of dish storage, where you take the dishes and then you push it on a stack and then it goes down. They've got a spring, it's spring loaded, so that if you take a dish off the top, the spring pushes them back up, right? So you're popping it off the top. Well, how do you put it on the stack? You're actually physically pushing it down, right? And so that's how I remember that it's always push, pop. I don't know. You pop it off the top. But anyway, I've got push. I've pushed the root on top. Now I go into a while loop so that I can take care of all of the rest of them. While the stack S dot is not empty, while it's not empty, then I've got stuff in the stack that needs to be processed. So I do exactly what I did here. I pop something off the stack and I process it. Then I need to process the left child and the right child, but as you've already observed, the way that you do that is by simply pushing the right child first and then pushing the left child so that you could go in the proper order. So I will take U, S dot pop, and then I will process U, whatever that means. And after I've processed it, I need to push stuff back on the stack. S dot push, use right child first. S dot push, use left child. Now, both of these as a comment here, assuming they exist, right? If you were to actually, if you go to actually program this, then you're going to have to check, is it null? And if it's null, then don't do anything, right? You're not going to want to push null onto your stack. And so that's why I'm putting it just in as a comment here, because I don't want to muddy this pseudocode up with a bunch of if-else statements. If U has a right child, then push it. If U has a left child, then push it. Otherwise, don't do those things. Okay? There is a nice preorder traversal, stack-based, no more than 4 or 5 or 6 lines if you include all the initialization stuff. Okay? Now, why does this help us? Let me go ahead and put this over to the side here, and let's go ahead and take that tree that we had before, A, or I'll rewrite the tree so that it looks better. Were there 2 children? A, B, C. Doesn't matter. I'll just do a new one. D, E, F, and say G. All right? Now, how does this help us? Right? Understanding this basic algorithm and how to walk amongst a tree, walk along a tree, has a lot of applications. And the one that you're probably interested in most right now is, what if these were corresponding to a Huffman tree? Right? And I'm interested in finding the paths from the root down to any leaf, because if I look at this this code right here, 0, 0 corresponds to D, right? Or D corresponds to 0, 0, whichever way you want to look at it. F corresponds to 0, 1, 1, because you're going to have to do this in Huffman coding. And G corresponds to 1, 0. Right? And the other ones, they're internal nodes. We really don't care about them with respect to Huffman coding. But if you want to, you can go ahead and output those as well. Right? How does this help us? Let's simulate what we did before with preorder traversal on this example. All right, so here's my preorder traversal. I've got A, right? And it's an internal node. It's not a leaf, so I would not end up wanting to output it here. I'll then go with the preorder traversal, go to B next. Again, it's an internal node. It doesn't really matter. But I went left. Maybe there's a way that I can track that by keeping track of a 0. Right? Then I go with a preorder traversal to get down to D. Again, I went left, so maybe there's a way of tracking that, keeping track of a string, going down to D here. Right? At which point, this is a leaf. Right? So this is, I'll draw it differently here. It's a D, it's a leaf. What if I've gone left, left? I've kept track of this with respect to my breadcrumbs or with respect to a string or something like that. So what do I output? When I process something, I output 0, 0, the current string that I've built so far. Right? And let me go ahead and keep track of that here, current string or something, 0, 0. Now, when I pop this off the top and go back up to D, I need to make sure that, well, I didn't go left anymore. It's not 0, 0. I'm at B. It's only 0. So what I need to do is I need to get rid of that last 0 that I appended to this string over here. Right? And I will continue my walk here. Go over to E. That's not a leaf, so I wouldn't end up doing anything. But I did go with a 1. So now my current string is now a 0, 1. I end up not going left, and so I don't append anything to that string. But I do end up going right, and I append 1, and I'm now at F, which is a leaf. And I output the current string, which is going to be 0, 1, 1. Hey, that looks familiar. 0, 1, 1. Right? I would backtrack, and this is the basic idea. Right? I would end up backtracking, and now I'm back up here at A. The current string is empty. Then when I go right, then I would append a 1. When I go left, I would append a 0, and I would end up outputting 1, 0 over here. That's the idea. How can we adapt this algorithm to do that? Right? Let's go ahead and fill in some gaps here. So at the top, when I push the root, then let me go ahead and create a string here. I've already used S, so what should I'll go with CW, standing for code word. And that'll be my stand-in for an empty string. Right? This is before I've begun. Right? Before I've begun, I'm at the root, so I have not created a string at all yet. All right, now let's go into the loop here. So help me out. I pop it off the top. I'm at a current node here. This is U. And then I process U. What does process mean in the context of outputting a bunch of code words? I will output the current code word, right? And associated with U's letter. right? So if you want to put that into a map for later retrieval, then you would map the use letter to the current code word, right? Simple enough. And you want to make sure that, I don't know about Python if it would end up being a reference or if it's deep copied, but be careful with that, because if you're manipulating a string and changing a string, help me out, anybody, Python, are strings mutable or immutable? I mean, of course you can change the contents of a string, but I assume that it would give you a new string. There you go. Okay, so you don't need to worry about it if you're using Python. Okay, but when I push the right child, I'll need to. I'm going. We're gonna have to have more. I should have figured this out before we came. But anyway, we're gonna have to push the left child. Where do we add 0 and where do we add 1 and where do we take them off? This is a good question here. So when I go to the right child, maybe I want to keep track of that as well. Yeah, something like going with a CW and then concatenate a 1 because you're going to go to the right, and then I'll push CW plus 0. And so I wouldn't output CW, I would output the string associated with U, right? So this is really nice in Python because you can push tuples. So I would, instead of pushing just a node, I would also push a string, a node and a string is what I would end up pushing into my into my stack. Right? And once you do that, then well, you're keeping track of not CW, but use CW. So you know what? I'm inclined to take 5 minutes and rewrite this so that we have it fully. S init stack. And forget about CW. What we're going to do is we're going to s.push t's root and an empty string. All right, so this is an empty string because eventually we're going to concatenate stuff to this. And when we concatenate stuff to it, then we end up pushing that string. So I'm pushing a tuple here. I'm pushing two things, a node and a string. Then while S is not empty, I will push, or I will pop the current node. In fact, it's a tuple, so let's go ahead and write it as a tuple. U, and I've already used S, so we'll go ahead and call it CW. There we go. S.pop. And again, it's popping a node and a string. Right? This is a node, and this is a string. There we go. Then the processing part here is going to simply just output. You know what? We're close enough to Python here. I'm just going to put it into a map. So what do you want to call your dictionary? Your code word map. Right? And a dictionary is going to be brackets. Right? And so what I'm going to do is I'm going to associate code word map. I'm going to put in the node's letter. So the letter, use, say, letter. And I will map that to the code word. There we go. And of course, there's more details here because you would only do this for the leaf nodes. So code word map CW, there we go. And then I need to push the right child, but when I do that, I need to push a tuple. Push use right child. And the string that you'll associate it with is going to be CW, CW, and then concatenated with a 1, because this corresponds to going right. And then when you push the left child, you concatenate CW and, 0. And there you go. And then eventually it comes out, and whatever the code word was that was pushed in with it, that eventually comes out of it. And so that's how you can use preorder traversal to walk along the tree. You're just keeping track of the breadcrumbs. Did I go left, right, left, right, left, right, 0, 1, 0, 1, 0, 1? Or did I go left, 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 0, 0, 0, 0, 0, right? You just need to keep track of those things. So remember that you can leverage preorder traversal, post-order traversal, in-order traversal if you really want to. You could do the recursive versions if you wanted to, right? And the reason that I reviewed that was because one, you're going to be probably wanting to use something like that for Huffman coding, but also let me go ahead and motivate what we're going to be looking at on Wednesday. What if I don't have a binary tree? What if I have a ternary tree? Right? How do I go about searching that? Well, kind of like a preorder traversal, you could go ahead and go root, left, middle, then right. Okay. Well, what if I didn't have a ternary tree? What if I had A, B, C, D, E? Well, I could go ahead and go with, root, then in some manner go in order for its neighborhood. Right? Now don't think of it as a tree anymore. What if I just had a node and it was connected to a bunch of other nodes? There's no left, there's no right, there's no up, there's no down. And then it goes off to the rest of the graph. Maybe there is even a cycle. It's not even a tree anymore. Right? How do I go about doing that? Same exact thing that we did with preorder traversal. Keep track of your breadcrumbs. If I want to go from let me get E, F, G, there we go. I'll start taking a walk. Go from A, what next node do you go to? There are lots of criteria that you can choose. I'll go to the lexicographically next one. And then I'll go from B to F, G, E. So these are my breadcrumbs so far. A, B, F, G, E. Right? At this point though, I'm looking back, that's where I came from. A, I've already been there. That's where I started my journey. So I need to start backtracking, right? And so these come out of a stacked data structure until I get back to where I started. Now, once I'm here though, right, I still need a way to tell, well, did I go everywhere else, right? In fact, where did I come from? I've already visited B, I've already visited E. How do I need to know, or how can I tell that I need to go to C or D? I need a little bit more than breadcrumbs. With a binary tree, it was really easy because there were only two possibilities. Go left, go right. Keep track of both of those and always go left first and then go right second. But there's no left, there's no right. There's just a list of vertices or a set of vertices. So I need to keep track not only of my current breadcrumbs to know where I came from and where I'm going, I also need to keep track of what have I visited before. And you'll note here that I kind of cross these out. That's how we're going to do it. We're going to color our vertices. White vertices are going to be unvisited. In other words, you still have to go to them. Gray vertices, are we AY or EY? I forget, English or American. EY, are we? Oh, we're AY, okay. Gray, visited, but not complete. Because I've gone down this path, and I haven't exhausted that path yet before I need to backtrack. And then the black vertices will be vertices that, I'll color it both ways here because I don't have a gray or a black. Black vertices are going to be vertices that are finished. Right? We don't want to go to them again because then we would be repeating work. You did want to go to them again on your first homework, right? Because you wanted to enumerate every single path in order to find a Hamiltonian path if one existed. But now we want to do it efficiently. We just want to do graph traversal here. So not only do we need to keep track of our breadcrumbs, we also need to keep track of the status of each one of these nodes. And the reason that we use white, gray, and black instead of, say, usually I would use like blue and red and white is because, well, it's very expensive to print color, right? So most books use white, gray, and black because they just use one color of ink, right? Okay, but we can. But I've got plenty of colors in here, so we can go with blue and red if you really want to. At the end of the day, it's just going to be true, false, or I don't know, an enumerated type basically if you want to go that direction, or a flag 0, 1, 2. Right? That's how I would program it.